In this video, I'm going to be going over scenario 5, asking the question, why does John Travoltage get zapped? So let's look at our objects, and we have John Travoltage. He has 10 atoms, so 10 protons, but he has a charge of -5. So I added 5 extra electrons to some of the atoms on John Travoltage. Now, since John Travoltage is a conductor, notice that those -5 atoms aren't just localized in one area. They're spread throughout my whole John Travoltage. So then I'm going to look at my other object. It's the doorknob. And it's a conductor. It has 5 atoms, so 5 protons. And since it's neutral, it has the same amount of electrons, 5. Now the doorknob is also connected to the door and the ground, which we could treat as just a relatively massive object compared to the doorknob and even to John Travoltage. So because it's so big compared to these two, we could treat it as an almost infinite supply or reserve of electrons. Kind of this idea that if I were to take a Dixie cup of water out of a lake, it really wouldn't change the amount of water in the lake. Or if I were to add a Dixie cup amount of water to a lake, it really wouldn't change the amount of water to the lake. Same thing with electrons. If I add electrons here, really wouldn't change the charge of this relatively massive object. Or if I were to take electrons to these objects, it really wouldn't affect the charge of the ground. So it's always going to be neutral, we'll say. All right. So in this situation, John Travoltage, that we just went over the before situation, John Travoltage is going to touch the doorknob. Electron affinity doesn't have any play here because, first of all, we don't have any insulators and there's really no charging by friction. But what we do have is two conductors. So this looks like it's going to be at least starting off to be like a charging by contact scenario where I have more electrons on John Travoltage than I do the doorknob. Right? There's just a negative charge here, neutral, neutral. Right? So nature likes to be chill. Electrons are going to want to spread out and even out. So they're going to jump over. And because these are conductors, these electrons can move easily through the materials, right, to the doorknob. Now the doorknob is not by itself though, right? It's attached to the door and the ground, that infinite supply of electrons. So the doorknob is going to almost act like a wire between John Travoltage and the ground. And this is not going to be a charging by contact situation. It's going to be a grounding situation where these electrons are going to flow through the doorknob to the ground, which is that infinite supply of electrons. So let me take my extra electrons here. All right. Now, by the way, as these electrons flow through John Travoltage to the doorknob, that flow of electrons, it's a bunch of electrons really, really fast just through the finger, and that's going to cause that zap that we see. And those electrons, once they go through the doorknob, are going to just enter the ground. Right? And since this is an infinite supply of electrons, the ground remains neutral. So I could just maybe just draw a circle for neutral. The conductor, the doorknob is neutral, and John Travoltage is also going to remain neutral as well. All of his extra electrons went to the ground. Right? Now, really quickly, just kind of think about what would happen if John Travoltage was positively charged, right? He was missing electrons here. Well, the opposite would happen. Instead of it being an extra reserve electrons, this would be an infinite supply of electrons. And electrons would just go up through the ground to make John Travoltage neutral if he was charged positive. So this explains that flow of electrons to the ground is why John Travoltage gets zapped.